All right, this is not going to be a terribly long video. What I want to do is talk very briefly about the right-hand rule we learned yesterday, review it, make sure you have it for this worksheet, and then introduce the other form of the right-hand rule, the more practical right-hand rule that we're going to be using pretty much from here on out anytime we don't have a wire. Wires are kind of rare in physics in reality. So a 15-second reminder of what we talked about yesterday. So let's say you have a current-carrying wire, and that current-carrying wire is going to have a direction. So let's say for right now the current carrying wire is running from my hand towards my shoulder here. I'm going to take my thumb on my right hand, not my left hand. The left hand isn't going to work. And I point the thumb in the direction the current's going. So from my hand to the shoulder, and I'm going to curl my fingers around the wire. So above it, the fingers are coming out towards you, and below it, they're coming in towards me, that is away from you. And so the curl of the circular field, you can see, comes around my thumb. And the thumb has to point in the direction. So if I don't do that, if I flip it around and I go the wrong way, then it's not going to work. Now, if the current were flowing this way, it's going to be the opposite, obviously, just like that. And current this way. You can see how they're flipped. And if I try to do this with my left hand, which is going to be a little contorted here, yeah, it doesn't. Nah, it's got to be a right hand, okay? Otherwise, you're going to be off by 180 degrees and embarrass yourself and, provide me some entertainment while you're taking your test. The other thing we can do is make a loop. So, simple loop here. Actually, make the loop a little smaller. I think it'll make more sense what's going on here. Okay, so I've got a loop, right? And if I take my finger here, let's say the current is flowing like this, right? From here to here. My thumb's going to go in the direction of the current, so I'm going to wrap my fingers. Okay, my fingers, no matter where I am on this loop, are pointing towards me. That is away from you. Okay, that means inside this loop, there's a uniform field coming from out here towards me if I run current through it, which is neat. Now, that's a solenoid. It's incredibly useful, and that's going to be a point of like a week of our class, because what happens when you start making twists of these, and can we predict like how strong the field's going to be, and can we make a really cool thing like a coil gun? And probably. Okay. That being said, this is what you need to answer like at least half of the worksheet. At least. Really easy. Thumb in the direction of current on your right hand. Curl around, out, in, easy. When you do that in practice, it might look something like this. I might give you something that asks you, okay, so here's a current. Draw me the field. Okay, well, let's see, my finger points this way. Looks like my fingers are coming out of the board above. So the arrow is coming towards me, so I only see its tip. I personally like to draw the outs with a circle around them to make them more obvious, so something like that. And then my ins, of course, are X's, because it's the back of the arrows. The last thing I see is the fletching, so in it goes. Okay, and so that would be a perfectly acceptable answer for what does the current in this flow? And if you forgot, of course, current flows from the positive to the negative. And so I may just give you a field and ask you to diagram it. But this stuff is pretty easy, honestly speaking, compared to what we've been doing. Certainly significantly easier than circuits. Now, you're going to have to twist your hand in some weird ways until you get used to doing it. Your right-hand rule may look something like this, and you're like, well, this is the... Okay, don't be afraid to contort yourself, and then realize there's probably an easier way sometimes. With the wires, give me your best effort. This is the stuff here that's, I think, the foundation. This is the stuff, once you've gone through it, it makes sense. Now, once you're done with this part, which may take you a couple minutes, it may take you half the class, I don't know where you're at exactly, because it's the first time you've ever done it. But once you get that down, you're going to realize it's a very limited thing, because there's all kinds of things where there's magnetic fields and particles that aren't wires. As a matter of fact, it's the more common situation. And this only works for a wire. I wish it would work for everything. It'd be wonderful, but it doesn't. And so we need to come up with a different right-hand rule, which I'm going to affectionately call the Physicist Gang sign. So if you want to look like the coolest person in the school, you're going to make this symbol right here. Thumb up, finger out, finger down. Right hand. If you look at it with your left hand, it's just stupid. No. Right hand, okay? It's got to be your right hand. Yes, I know you'll be writing your test. You'll be sitting here looking at your left hand. You'll be like, I'm getting... No, you're wrong. You've got to go with the right hand. Thumb up, finger down. Something like this. And you'll notice, when you look at it, how I orient it, these are at a right angle to each other. They're like the corner of a room. So let's say I am looking at the edge of a wall. Of course, I've got my z-axis up. I have a field x out. I have a field y out. Well, my fingers, to the best of my ability, are going to make that shape in some way where these are all at a right angle to each other. And it's easier to do it with my hand here than it is to think about it in my head because it's 3 dimensions and it's twisting. I guarantee you, at some point you're using this, you will end up all twisted around until you get used to just thinking about it a little bit and flipping your hand around. It's okay. Now, each of these fingers represents something. One represents the direction of motion of a charged particle, like an electron, a proton, a charged body, it doesn't matter. One's going to represent the field direction, the B, the X's and dots from our wire. And one is going to represent the, resultant vector. See, this is a little confusing. Remember that F equals ma, so mass times acceleration. The proton's got a very small mass. It turns out the force and the acceleration here are not parallel. It's not like Newtonian physics where I've got a block and I push it and they move in the direction I push. It actually moves orthogonally through the vector cross product, something that you'll learn if you keep studying physics, to the field. So it moves in some relation where everything needs to stay at a right angle in 2 dimensions instead of 1. Right? A 1-dimensional right angle is easy. A 2-dimensional one's going to require you to learn this trick. Now, it's easy enough to make a right-hand rule. I want to explain it, though, instead of sitting here and twisting my hands and be like, look at my hand. No, I want you to actually see a diagram of it so you understand how to use the right-hand rule. And for that reason, I'm going to cut here to a picture and voice over a little picture. So hold tight with me for 1 second. All right, so we're over here now. And if you're someone who doesn't like having tabs open, my apologies, I guess, or something. I'm not really sure. Anyway, here's a quick sketch of the right-hand rule. And hopefully you can see how that is the same as this, right? Everything is at a right angle to each other, more or less. Now, your 3 fingers, your magnetic force will be your thumb. Your charge will be your first, and your second finger, your middle finger, will be the field line. So, charge, direction, line. Now, these 3 things together are it. So what's going on in this picture here? I've got the moving charge, and it's moving across the screen the way it's showing, yeah? And everything's mirrored, so I have to be thinking. And the magnetic field here is starting in the screen and coming out towards you. So my force here, my magnetic force, everything is moving this way, and the magnetic field line is pointing out, which means my magnetic force here is pointing up, which should make some sense. I don't know if you can see that, but see how my thumb points up? So the resultant vector is actually what we call normal to both things, to the line coming towards me and the line moving out, like that, right? The resultant vector is perpendicular to both things at once. And it's hard to show because 3 dimensions are hard to think in. But this is really about it. Now I'll put this exact drawing on your notebook. But let's take a look at an example problem or 2. All right, so let's start by looking at this one, which I think is pretty straightforward. I've got a magnetic field here, these dots, and they're dots. They're pointing towards me out of the page. So right now you're looking at the projector screen, right? And there's a magnetic field being projected from the screen towards you. So imagine the field's coming directly at you. Over here, I have a magnetic or an electric charge that's moving across that perpendicular on the screen. Okay, so I've got stuff coming at me. So drop number 1 at me. And I've got something coming along. And there we go. Now that's backwards to you because you can't see my 3rd finger, so I'm going to turn it a little bit. You can see 1 arrow, the magnetic field, pointing towards me. 1 arrow pointing in the same direction as the field is going down. Of course, my camera here is mirrored because of the nature of a laptop. So you have to assume that's coming towards the direction that it's supposed to. And the thumb up. And if you doubt that, you can just look at it. If your fingers look something like this, and you can see these 2 fingers facing you right now. So when you're looking at your own hand, you should see these 2 fingers facing you, your pinky and the other one. Well, that's going to tell you you've got it right. If you can see that orientation, how this finger pointing at you is the magnetic field, how this one here matches, and this thumb up represents the net of these 2 things, then you've got this. Now, I get it, it's difficult. It's hard. You're like, which way do I try? Okay, we're going to get lots of practice with it. This is the exact same question I just asked in the last picture. And the point is you have to be able to translate between these things. And yeah, it takes a little bit of time. But I firmly recommend just taking your finger and literally laying it the direction the arrow is pointing, right? And then working from there. Okay, the field's in or out. Okay, let's do one more example here and then I'll set you free. All right, so this is a slightly more complicated example. First, I've got a magnetic field over here, which we call B, which points from the left to the right. And I have a charge going in. And I know it's a charge because it's the only one. And I got to keep my fingers in this orientation. And remember, charge, field, result. My thumb will always be my answer. So see, the charge is pointed at the screen. So I'm going to take my fingers, point it straight at the screen. Okay, I'm going into the screen, and my other finger's pointing the wrong way. Now, and here it looks like it's the right way. My middle finger looks like it's matching it. Remember, my screen is mirrored. So for me to get it right, I'm going to twist my hand, and you see my thumb points down, right? So I would say the field is down here. And yeah, I wouldn't, if I'm taking this test, I wouldn't contort myself that way because, well, I've done enough of these problems. I would just look at it and be like, okay, I'm down. That being said, you're going to be sitting here twisting your right hand around. And it's going to be tempting, as I said, writing with the right hand to sit here and do it with your left hand. It would be so easy. Look, boom, done. But that's not right, and be careful. Okay, let's just for a second pretend, you know what, it's not actually a arrow field in. Let's say it's a field in instead of a field out. So here we go. And why aren't you working? Okay, we'll do it a different way. Okay, so now it's a field out, right? Dot instead of an X. Same game, except now this finger needs to point at me, and this finger needs to come along, and twisting my finger, you can see the thumb is up. So by doing it, all I did is I flip from a down for the into the page, or for the into the page, and now I have an up for the out of the page. It flips 180 degrees, which is logical if you think about it. You're probably going to miss some of these. I'm not going to lie, the right-hand rule seems really stupid. It almost seems like I'm just trying to be like a puppet master, almost like, move your hands around and see if you can play my game. I get it. I hated it as a student. It's incredibly easier than the alternative, which is learning about a week of vector calculus. This is better. Yeah, you have to think about it a little bit, but once you get it down, it's second nature. Now, when you're doing vector cross practice, when you're doing this right-hand rule, the biggest rule is don't leave this orientation where your two fingers are touching your palm. As long as your two fingers are touching your palm and your three fingers are at a right angle to each other, you can twist your hand however you need, and your answer will be your thumb if this is one part and the other. We're going to use this being the charge and the field, although you could honestly flip them and get the same answer. And that will take care of it from there. So I want you to try this on the worksheet, and I get it may be a little tricky. I'm going to collect the worksheet tomorrow. We'll do some of it together. Give it a good faith effort. What I don't want to do is come in and see it be blank, because if it's blank, all that tells me you did is give up, and that's not really what this is about. If you have any questions, feel free to kind of jot them in the margins so you know what you're doing. Like, ooh, I thought this one was easy, but this problem here, I don't get how you twist your hand, and I'll help you. I don't plan on giving a quiz on it tomorrow. I plan on doing a bit more work with it, although you will have a quiz on this by the end of the week without a doubt. But in the meantime, this is all you need to do. Now, if you do finish the worksheet early, you'll please respect the fact that you have a sub and that sub is giving his time or her time to help you. And so, of course, feel free to work on what you need to get done if you do finish the packet respectfully and quietly. So, otherwise, I'll see you tomorrow, and I hope you have a wonderful day.